Now we want to look at some of our vocabulary, our statistics that we're going to use to help us understand distributions and that sort of thing. So we've looked at histograms and distributions and all that, and so suppose I have a population or two different populations, you know, one that maybe looks like that and one that looks more like that, and you know, as I look at them, what's different about them? Well, let me add some numbers. You know, maybe this is down here at -10 and this is up here at 10 and this is 0 and that's 1. Then as I look at these two things, well, to characterize them pretty quickly, if I kind of told you about where the center was, whatever that means, you know, that would be helpful. You know, I tell you, oh, well, it looks like the center here is maybe at around 0 and the center here is at around 1/2. And then if I could give you some idea of kind of how wide the distribution is, how much does it spread apart? And here, you know, the middle is 1/2 over here, but it only spreads to 0 and 1, and that's it, it stops. Whereas the one over on the left here, you know, the middle's maybe around 0, but it's spreading at least to -10 and 10, maybe more, because, you know, maybe it just keeps going for a while. And so to give you some idea of maybe the center of the distribution or the population, and kind of how wide it is or how narrow it is, if I could give you some numbers that would help you know that, then, well, that would tell us a little bit about the population and the distribution. And so we're going to start with the center part, and we are going to look at measures of central tendency. Okay, ways to talk about the center of a distribution. And we will look at really two ways, but we'll mention three. The main one we will use for most everything will be the mean, okay, or we could call it the average. And that most people are pretty familiar with. Then, so that is one. A second is the median. And then the third is the mode. We won't really deal with that much, but I just toss it in there. It is in the textbook. They mention unimodal, bimodal, multimodal, all those kinds of things. I'll let you read about the mode. We're not so worried about that. Pretty much the things we care most about in this class are unimodal, kind of like our distribution here on the left. We care mostly about that. Okay, so mean or average. I think most people know what's going on there. Suppose I have some data that I've gotten, and you know, maybe it's 1, 1, 2, 3, 3, 3. How many do I have there? 1, 2, 3, 4, 5, 6. Sure, that's good. So, so there is. Well, let me go one more. We'll do a 4. So there are 7 data points, and if I want the average of that, now the average, if it's the population, now probably if I just have 7 numbers that look like this, that's probably not my population. It's probably a sample, but I don't know. I don't really have context here. So we're going to look at both, and if I want to talk about the population mean, so suppose that were the population, then I would use the Greek letter mu. It looks kind of like a U with a little extra, a flourish on it there. But that's mu, okay, M-U, mu, Greek letter mu. And, well, it's what we always knew it was. Okay, I'll take 1 plus 1 plus 2 plus 3 plus 3 plus 3 plus 4. Divide that by my 7 for the total number there. And my population, if this were a population, then my population mean would be, well, let's see, I get 1, 2, 4, 7, 10, 17 over 7, whatever the heck that is. Okay, so 2 and 3 sevenths. But I get 17 over 7. Now, that's population mean. If it's a sample mean, so I took a sample mean, we'll often call that the average, is I use an x with a bar over it, x bar. And, well, that's just the same thing. 1 plus 1 plus 2 plus 3 plus 3 plus 3 plus 4 over 7, and that's 17 over 7. Okay, so there's the mean. Now, the median, again, population median and sample median are really both the same idea. And the median, so median is the middle number. Now, for continuous populations, this can be kind of hard. You need some calculus to deal with it. But if I'm just talking about a sample, discrete sample, or a discrete population, pretty straightforward. I had 7 numbers here, right? I had 1, 1, 2, 3, 3, 3, and 4. Now, if I just go through, I have to put them in order like this, smallest to largest. And then if I just number underneath them, 1, 2, 3, 4, 5, 6, 7. Okay, where is the middle number? Well, it is right there, right? There are 3 on this side, 3 on that side. And so there is the middle number 3. And so in this case, the median is 3. Now, if I wanted to start with an odd number of numbers. If I have an even number of numbers, so suppose instead I had 1, 1, 2, 3, 3, 3. In this case, you know, as I count 1, 2, 3, 4, 5, 6 numbers, well, if I take the 3 on this side and the 3 on that side, oh, there's not a middle number. There's nothing there. Well, so what you do then is you take those 2 numbers that are closest, that are touching, touching, well, I don't know, probably, hopefully not inappropriately, but they're next to each other, and they're at the middle. Then, in that case, the median is the average of those 2 numbers. So 2 plus 3 over 2, or 2.5. Or 5 halves. So the median, pretty straightforward, but you absolutely have to sort the numbers first. So you sort the numbers, and then you just look for the middle. If there is a middle number, you just take it. And notice that that 3 is the same as those 2 3s over there, not the same as that 2. But if there is not a middle number, because you have an even number of data or population, then you take those middle 2 numbers and just take their average. So there's our median. Now, what we see is that there are reasons to use each of those. Often, if you see things like income or housing prices, things like this we'll often use, actually, to describe them, median. Now, let's look at a very simple reason for that. So let's take some incomes and let's do it in dollars per hour. And so suppose I just have maybe 5 people, and I say, okay, this person makes 10K, or no, hourly wage, not 10,000 an hour. Ooh, that would be nice. But you know, so suppose I have a person making $10 per hour, another person making $10 per hour, somebody making $12 an hour, somebody making $14 an hour, and then somebody making $64 an hour. Okay, so if you look at this, if I take the average, my X bar, notice that, well, okay, I've got my 10 plus 10 plus 12 plus 14 plus 64, all divided by 5. So that's 20, 32, 42, 46, 110, I think, over 5. And it says, hey, on the average, they're making $22 an hour. Well, that sounds pretty good. You know, you say, oh, hey, I've got these 5 people, and on the average, they're making $22 an hour. Wow, sounds great. But the problem is that this 64 is so much higher than the rest, it kind of skews the data. Whereas if I use the median, and I don't have a symbol for the median, if I use the median, well, that's 12. And as you look at that group of 5, you know, I really think that the 12 is a better description than the 22 as to, you know, sort of what's the average type person. This is where you got to be careful with the word average. You know, if you think of the word average can be both a general term for a central tendency. Okay, I just want a central tendency to this, and so the mean, median, and mode could all be considered types of averages. Or average can mean mean. Wow, that's a lot of mean, you know. But yeah, it can mean the word mean. And usually when you use it, you're using it as a synonym for mean. But once in a while, you'll see things that use average in the more general sense, and when they talk about average, they may actually quote a median or something like that. And so you have to be a little careful about that. But in this way, you see the median, it takes care of the fact that this one huge number was really throwing off the rest of the data. So, you know, mean is a fine number, median is a fine number, but they both have their pluses and minuses to using them. And so, you know, when we have things like the 64 that we might call an outlier for the rest of the data set, then median, you know, is kind of nice. You know, housing prices, same thing. You could have an area where almost all the houses are like between $100,000 and $200,000. But all of a sudden there's just this one small neighborhood where the houses are, you know, over $1 million, you know, they're multi-million-dollar houses. Well, you know, now if then you talk about the bigger region and you throw in the multi-million-dollar houses into a mean or an average like that, well, it's going to make it look like home prices are much higher than they really are. Whereas if you use the median, then you're not as affected by those either really large or really small numbers out on the edges. Okay, so there's a reason for median versus mean. Okay, but typically in this class we're going to use mean, or, you know, the what we usually think of as average, because our calculation techniques use that, and so that's the number we want. All right, so that's two of our statistics, our central tendencies. Now I'm going to try to start another sheet. Okay, there we go. And now we're going to look at more of this idea of spread. And there we have variance slash standard deviation. And I'm even going to toss in slash standard error. And then our other one, so that's one type, and then our other one is inner quartile range. Inner quartile range is a little less well defined for small numbers of data than variance. Variance is very well defined. So we're going to start there with variance, standard deviation, and standard error. Okay, and we're going to use the variance. Now here it really does matter whether I'm talking about a population variance or a sample variance, and we'll see kind of intuitively what's going on here. So a population variance, what do we do? Well, again, let's see, if I go back to my numbers here, I had what, 1, 1, 2, 3, 3, 3, and 4. So, okay, so I had those numbers 1, 1, 2, 3, 3, 3, and 4, and we know that x bar for that was 17 over 7. So when I look at variance, what I'm asking is sort of how spread out the data are. Well, a good way to check that would just be, one number to try to do that would just be to say, well, okay, I'm going to look at the differences. I want to look at the average. Okay, so average, we know what average is. The average distance between each of my data points here and the average itself. Okay, this is somehow sort of the middle of the data. How spread out is it? You know, are the data a long way from that number, or are they really close to it? And so we could take that average, and so I could take 1 minus 17 over 7. And I could take, again, 1 minus 17 over 7. And I could take 2 minus 17 over 7. Now I'm leaving some space here because we've got to do some stuff. 3 minus 17 over 7. 3 minus 17 over 7. And 3 minus 17 over 7, and then finally 4 minus 17 over 7. Now, I could add those up, so add them all up, plus, 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 right, all in there, and divide by how many there were, so divide by 7. And great. Now, the problem is if you do this, you're going to get the number 0. Okay, the reason you're going to get the number 0 is that if you move things around, what you find is that we just took all the numbers up here and added them up. Oh, well, that's how we got the 17. And so we would get 17 minus 7 times 17 over 7. Oh, but 17 over 7 times 7 is 17. So we'll get 17 minus 17 on top. It'll be 0. Okay? So that doesn't get us anywhere. Oh, well, let's take the absolute value. Now, what we find, people have studied all this and so forth. Well, what we find is, well, actually, instead of taking the absolute value, so I'm not using straight lines here, I'm using parentheses. What you want to do instead, another way to just get a bunch of positive numbers so that we don't cancel everything out and get 0 is, oh, well, we could square those instead. Now, why do we do that? Well, because it works. You know, it's a mathematical thing that we found works very nicely. So our population variance, in terms of sort of a formula, is what we're doing is if our data are xi, okay, so we had 1, 1, and so forth. So the first data point, x1, was 1. The second one was 1. The third data point, x3, was 2, and so forth. So this is just a nice, quick way to say, oh, I've got a bunch of data. And how many data? Well, we had 1 to 7. But, well, in general, I have 1 to, you know, some number n. What we say for our variance, and if it's the population variance, we call it sigma squared. Okay, so this is sigma squared, and that's the population variance, kind of like mu was the population mean, equals. And what we did here was we took each data item minus the overall average. Well, and actually I should use not x bar but mu. We took, for each one of those, we squared them. Now, how do I say do this for each one and add them together? Oh, we use actually an uppercase sigma. So that's just a math symbol saying, okay, take all our data, do what we did up top up here, and so the sigma means sum them all up or add all these like things together. So I'm taking each data item minus the population mean, squaring it, and then dividing by n, how many I had. Okay, that's what we did up here. That's the formula, and so that is population variance. Okay, now the only difference if we move to a sample variance, and this is very important because it changes, it matters, but the only difference here, we change it to s squared. We do that same thing. We just add up our, in this case, data instead of our population individuals, minus x bar. Okay, so that's saying our sample mean squared. Now, here's the big difference, divided by n minus 1. Okay, so up here, we divided all that by 7. Down here, we would have taken that same thing. We would have had our 1 minus 17 over 7 squared plus all that stuff plus 4 minus 17 over 7 squared, but we would have divided by 6. That's the difference. Now, again, you can kind of intuitively get an idea of why that would be the difference. Okay, what are we doing when we take a sample mean? What are we really doing? Well, we're trying to estimate the population mean. Okay, well, since it's in the center, you know, intuitively it seems reasonable you could do it pretty much the same way. But here, with variance, we're trying to estimate, say I have a population that looks like that. I'm trying to estimate this spread out here, but what we know from looking at, say, this distribution, this histogram, is that getting data from out here is going to be rare, right? This doesn't happen as often. The frequency is much lower out here. And so we're going to get mostly data from in here. Well, if that happens, you see, we're not going to realize how much our data can really spread when we take this sample. You know, because generally, if you have a population that looks like this, with most of the population toward the middle numbers, then, yeah, the extremes you aren't going to see very much, right? I mean, you know, how often, you know, we have people in the population who are over 7 feet tall. Unless you go to a basketball game or a volleyball game, you know, when do you see people that tall? You hardly ever see them that tall. So if you just took a sample right? You might not ever even realize we had people over 7 feet tall. And so, if we're trying to estimate the population's spread, okay, the population variance up here, sigma squared, by taking a sample and getting this number that we have here, right? So we're trying to estimate it. Then it does seem like we should try to fudge it up a little bigger than we see, right? If I never see 7-footers, how am I going to actually estimate the fact that there could be 7-footers? Well, by fudging it a little bit. And notice, you know, I'll just take a couple numbers here. If I were to take 12 divided by, let's not do that. Let's take 30 divided by, still not do that. I got to pick the right numbers here. 42, that'll work. If I divide that by 7, right? So suppose that numerator had been 42 and I divided it by 7, I would get the number 6. Okay? If I divide it by 6, on the other hand, I get the number 7. So when I divide by a smaller number, and n minus 1 is smaller than n, when I divide by a smaller number, I get a little bit bigger number. And so by using the n minus 1 in the sample variance, we're causing our estimate to be a little bigger than it would be if we used n. And statistically, looking at it, you know, lots of mathematicians over the years and so forth have looked at it, that is the best way to go. It's best to use n minus 1. I mean, we could have made it bigger by using n minus 2, by using n minus a half. We could have done all sorts of things to make it a little bigger. The way it makes, you know, the best answer, it turns out, is to use n minus 1, and so that's why we have that in the formula. But so the takeaway here is that sample variance is different than population variance, okay? So that takes care of the variances almost. The other thing, remember I had said standard deviation and standard error. Well, standard deviation, so standard deviation is just the square root of the variance. Okay, so you either have, if you have a population standard deviation, you would call that sigma. That's the square root of sigma squared. If you have, so this is population. If you have a sample, then you talk about S as the sample standard deviation, and that would be the square root of S squared. So that's all standard deviation is. And then finally, standard error. Okay, standard error is the standard deviation. Okay, so it's really the same thing. Standard deviation of a statistic. So if we talk about the sample mean and we get lots of different sample means, then that will have a distribution. Remember, that's a sampling distribution. So another way to look at it is the standard error is the standard deviation of a sampling distribution. Okay, so if you hear standard error, you would just kind of assume, oh, they're just talking about the standard deviation of some particular sampling distribution. And again, for us, that's almost always the sample mean. That's what we care about as the sample mean. And so when we talk about that standard error, it's the standard deviation of the sample mean. Okay, so that's standard deviation. Now I'll add one more page here for the inner quartile range, or IQR, inner quartile range. Now, inner quartile range is a lot like the median in the sense that it is very stable. Okay, like the median. Okay, if you start adding numbers to a sample, the median doesn't tend to change much, but the mean might, right? The average might, because you might add a really big number and that will change things all of a sudden. But we saw that with our example of hourly wages, median was more stable. Well, the interquartile range, IQR, is also a more stable measurement than the variance. Okay, so sort of the same idea. What we do with the interquartile range, we find the 25th and 75th percentiles, or where the quartiles are. So I'm going to use a few more numbers in this case. Okay, so here are a bunch of numbers. I'll start numbering how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure, we'll go with those 10. Now, so this is where, though, the IQR is a little less well defined, and we'll see why here momentarily. Okay, so what I'm going to start with is to find the median. And okay, so there are 10 numbers. I need to go between the 5 and the 6 number, and so my median here is 3.5. Okay, because it's the average of 3 and 4. Now, what I need to do for the interquartile range is I need to find the median of this side and the median of that side. And now the way I have it here, right, is if I if I say, well, I used the 3 and the 4 here, those two, if I use those to find the median, then I don't want to put those in. Oh, okay. Actually, you could say that. And we'll look at an example why here in just a moment. You might say that. Or the other is that since, this split this definitely in half, then I'm going to keep that 3 and that 4 in there to find my median of each side. But you see, it matters. It will change it slightly, most likely, at least for very small samples. Because here, if I keep all 5 numbers, then there is my median, and I would call that Q1, or the 25th percentile, 25th percentile. And here, it would be the 7, and so there's Q3, the 75th percentile. Okay, in other words, about 25% of the data is above that and 75% is below, and down here, 25% is of the data are below and 75% above. And the median is the 50th percentile. Okay, so I do those, and then the interquartile range is very simple to compute once I do that. There's very little calculation to do in these. It's just the Q3 minus the Q1, and so in that case, it's 8 minus 3 equals 5. Now, but you see, if I had said, oh no, you have to throw out those numbers because we used them to find the median, then when I look at this, you see I've got just 4 numbers, and I have to take the average of the 1 and the 2, and so in that case, my Q1 would have been the 1 plus 2 over 2, or 3 halves. And same sort of thing up here. It wouldn't change it because I'd take the average of those two, and I'd still get just 7. Okay, so Q3. Oops, did I do something wrong here? I said 8. Sorry, Q3 is 7, and so this is 4. Sorry about that. I think I mentioned in a video, or not in the video, but I'd made a mistake in a previous video that I'd said sections, I think 1.3 and 1.4 when it was really sections 1.4 and 1.5. And then I said in the intro to that video, in the writing, I said, it won't be my last mistake. There you go. I was right. Wasn't my last mistake. And this one won't be either. So once the class is done, all the grades are in, and everybody's satisfied I didn't make a mistake on their grades, or if I did, we fixed it. Then once all grades are done and all that, then I'll be done making mistakes. Okay? But until then, yes, I could make a mistake. So up here, this should have been a 7, not the 8. It should have been 7 minus 3 equals 4. Now we come down here. This is 7 plus 7 over 2, which is just 7. But you see now, if I do it this way, I get an inner quartile range of Q3 minus Q1, 7 minus 3 halves. Well, that's 14 halves minus 3 halves. That's 11 halves. I get different answers. They're similar. They're really close. I mean, 4 and 11. 11 halves? 3 halves. 7. Did I really mess that up that badly? I did. Wow. Sorry, I'm not going to do this whole video over. But notice here, I did the same thing there. That should have been 7 minus 2 is 5. Wow. See, again, not my last mistake. Okay, so very, very sorry about that. I apologize. Q3 here, was the 7. Q1 here was the 2. 7 minus 2 is 5. And then 7 minus 3 halves is 11 halves. So I did this one just fine, but I sure screwed up the first one. Okay? Now, so given that, for one, if you make a few mistakes, not a big deal. I make mistakes. Now, but notice what happened here. I made a mistake. I made 2 mistakes. And I caught them both as I did more work. Okay, because I kept thinking back, I looked back at what I had before, and I knew I should get about the same answer. And so when I got this 7 and knew, of course, that was 7, I noticed that I'd put that 8 there. Oh, well, yeah, obviously that had to be wrong. I looked back, and yes, it was wrong. Then I caught that I'd done the 3 and the 3 instead of the 2. So this should be 7 minus 2 for this first one equals 5. I caught that because I had gotten an answer of 4 here, and here I got an answer of 5.5. And I thought, no, they aren't that far different. I mean, they should be close to the same number. And yes, they were. I had just made a mistake, and I had used these bottom numbers where I was just counting instead of the actual number. So see, I can make bonehead mistakes just like anybody, maybe better. But often I catch my mistakes, not always. And if you ever see something that you think I made a mistake in one of these videos, let me know, ask a question. Okay, so I very much apologize for making that mistake, but we've got it right now that I should have had 7 and 2 equals 5 there, and then here 7 minus 3 halves. The big takeaway is that depending on how one defines the inner quartile range by defining these particular quartiles, Q1 and Q3, you can get slightly different answers. Now, for this course, what do I want to do? So for this course, what we'll do, if we have an even number of data, okay, keep all data for Q1 and Q3. Okay, keep them all, so do like we did in this first one. Well, sort of like we did in the first one. Do it right the first time, okay? That would be helpful. But do it like we did this first one. Don't worry about getting rid of those numbers there. And right at the moment, I don't remember what your authors do. But again, it's one of those things that we just need to make a convention, and that's what we're going to do for this course when I have you calculate interquartile range. Now, I'll only have you do that a couple times, but just for those couple times, that's what you need to do. And again, because this interquartile range is all built on various types of medians, you know, median there, and then that's a median, and that's a median, it's a lot more stable when you start adding different numbers in and so forth. They don't tend to change the numbers a lot, especially if you have quite a bit of data. Whereas with variance and standard deviation, those can change greatly if you put in either really, really small numbers or really, really big numbers into your data set as as the sample gets bigger or something like that. And so again, if what you're interested in is a reasonably stable number that doesn't keep changing a lot, then you would probably use interquartile range here, IQR, to talk about your measure of dispersion or measure of spread. But again, for our calculations, as we go through the rest of this course, we're going to tend to use standard deviation. Okay, not actually variance. We're going to take that square root and use a standard deviation, standard error. But that is because it fits the assumptions we're going to have for our data. Okay, so I think that does it for this one. And this was really, really long, so maybe I will try to separate it. I don't know that I can, but that is our statistics.